Okay, hello class. This is video. As you know, when I start recording these videos, I look into my big monitor over here instead of the small monitor. Of course, the camera is right up here, of course. I apologize for this visual noise. Don't know why it's here. Before I forget, I want to make sure I tell you that I hope all of you are well and you have no sick folks in your families. Or if you do, that they get over this really quickly. Okay. Uh, I have tried several times to figure out how to bring these screens up and have them ready when you start seeing the video, but I can't figure out how to do that. So it's going to take me 2 or 3 minutes to get all my screens up. If you want to fast forward and look to where I start, that look like I have the screens, I'm going to get 3 screens up. One is some handwritten notes that I put together myself on grid paper. The other is the tables. I'm going to pull up some of the tables to look at it. And the third is going to be OneNote, where I can do some sketching on my Wacom pad. And as you know, the sketching is not very good. Apologize in advance. Okay. So what we're going to be looking at today is I'm getting ready, trying to get you ready to do test 3, which is on chapter 5 and 6. And I know you haven't had any homework on chapter 6 yet. So the test is going to be combination homework and test. And the reason I think this will work fine is because I'm going to give you plenty of time and plenty of coaching. In fact, my goal in this is for the work you do on that you've done on homework number 6 and the work you do on test 3 will actually, since I'm sort of combining them, they will be actually less work on you, because I know you're all busy and trying to adjust to this online stuff like I am. I'll let's see. Anyway, there'll be more information about that in the email that will tell you how to get to this video. So I'm going to get rid of this. All right, I'm going to start pulling up the screens. Like I said, this takes just a little while. So looking for this PC, found that. I know you can't see it yet. Look at my drive, look at my files, look at my thermal files, and I'm going to pull up what I'm calling a test 3 prep package, test 3 preparation package, which is what we'll be looking at. Now I'm going to share the screen and see if you should be seeing this, and I'm going to put my mug down here in the bottom right. Now, I'm going to see if I can pull up another screen, tables. Now I'm going to try to put the, whoops, put the tables here and put those handwritten slides that I put together here. Now I'm going to go down at the bottom and truncate them a little bit so I can see. Now, I'm going to share this and see how it looks. Okay, that looks pretty good. It looks like you can see both of those screens, both of those files. Now I'm going to bring up OneNote. This gives me a little trouble sometimes because it looks like it's awake. Let me see if I can share this screen. It will have OneNote on it now. So if everything works the way it appears to, you can see all 3 screens we're going to be talking about. So let's get right to it, as they say on TV. All right, here's the slides. Maybe I will put myself over here in the middle, maybe down. All right. So we're we're looking at chapter 6 now, specifically the second half of chapter 6, where it talks about entropy change and control volumes, are real world type problems. And I'm going to look at 3 situations today or tonight or whenever you view this. That's ideal gas compressors, air compressors, nitrogen compressors, that sort of thing. Then we're going to look at power cycles a bit, power generation cycles, where the main output is the turbine. Turbine is powered by steam to drive a generator and produce electricity. So that'll be the second. Then the last thing we'll look at is heat pump, a heat pump cycle. Now, if you'll stay with me and hang in with me on these cycles, I think you'll be really prepared to do well on the test. By the way, I want to make clear this packed test I'm going to give you, this combines the homework task and the test, yes, but it's going to be counted as test 3 only. No homework counted in it. It'll be strictly test 3. So important you do well, but my intentions are to cover this material so well that doing well won't be hard for you, or if you apply yourselves, you can do very well. All right, first off, let's get started. Let's look at an ideal gas compression. Now let's look at OneNote just a little bit, and I'm going to try to draw a TS diagram here, and it's not going to look very good, I know. Right, here's our dome. Not a very good dome, is it? All right, and this is temperature, and this is specific. By the way, we'll be looking at pretty much, it's not a 5, that's an S. TS diagrams pretty much all the time now. Let's try to draw a couple of constant pressure lines here. They look just the same as they did on the TV diagram. Let's draw another one up here. All right, and of course this is a lower pressure here. It could be one bar here, and this could be 100 bar up here. So when we study ideal gases, this is of course a 2-part mixture here, or a two-phase fluid. It could be 2 phases, like water can be steam, vapor, or liquid. 3 states we sort of are a mixture. But ideal gases like air and nitrogen, they live way out in here, and at least they exist out in here whenever they have a thermodynamic importance to us. So if I come way out here and I start drawing constant pressure lines, well, of course, they're going to look just like this. This is one pressure. This is it should be a straight line. So when we do we do a TS diagram, we look at a couple of pressure levels on a TS diagram, we're going to see something like this. Okay. So here it shows a compression process, a TS. Now this is specific entropy now. And we're going from pressure level 1 to pressure level 2. We start off at state 1 and we compress, and theoretically, if we've got a really good compressor, we will call our compression isentropic compressor, isentropic reversible adiabatic compression. And this is our ideal compression. So we go from state 1 to state 2 isentropically. So you'll see the entropy axis, we're a straight line up the entropy axis. So entropy at 1 is entropy at 2. And we do that because that's our baseline. We know we're never going to get that good, but how good a compression we got will depend on what the isentropic value is. So our actual compression does something like this. It'll start at the same point, 1, a lower pressure, and compressed up to the higher pressure or discharge pressure or preset pressure. At Eaton, our air compressors were set to discharge at about 125 psi, and of course they took in air at 1 atmosphere. So there's the ideal process. Entropy is constant, but we know entropy always increases. Well, entropy can increase and decrease in a heat transfer process, such as QH or QL happening. In work processes like turbines, pumps, and compressors, entropy is always going to increase because that's the measure of our irreversibility, how much friction we got in the process, and so forth. Friction, internal leakage of the air from the high pressure region back to the low pressure region during the compression process, heat transfer, these are all irreversibilities. And it's interesting to look at this little triangle here. In my opinion, it isn't pointed out in the book but this little triangle here represents the heat transfer due to the irreversibilities. Eventually, all these irreversibilities manifest themselves, or most of them, in the form of heat transfer. We call it adiabatic isentropic reversible compression. That's our ideal. That's what we measure against. What we actually get is an increase in entropy. And this increase in entropy is due to irreversibilities, and most of these irreversibilities, 90–95% of them, actually are realizable, are visible, or measurable in the form of heat transfer from, in this case, from our compressor. So our compressor gets hot due to the friction, other losses inside the compressor, it creates heat. That heat goes to the shell of the compressor, and it's eventually convected away. Or the way we did our compressors at Eaton, they were so big that, and they high performance, and we couldn't depend on atmospheric air to cool them to take this parasitic heat transfer away. So we actually used cooling water, and inside the compressor itself, and this heat of compression was carried away by the cooling water. And as we know, I mentioned several times, when you compress the air, what you're trying to get is a higher pressure air that you need in your factory for your processes or to drive some pneumatic machinery or whatever. What you also get that you don't really want is the increase in temperature. All right. That's just a fact of life. That's called the heat of compression. That's a good fill in the blank. Okay, let's look at this. The isentropic compression hits this constant pressure line at a lower temperature than the actual compression process does. So we label that as T2S, and then the actual temperature is T2. So if we've got a problem to analyze a compressor like this, they generally fall into two categories. In both cases, you're going to have to find T2S and T2 in order to be able to analyze the performance of the compressor. And we know for air out in this region or any ideal gas, the enthalpy, what we need T1 and T2S, or T2 and T2S, and we have T1, what we need those T's for is to look up the enthalpies. Because H1 is a function of temperature 1, H2 is a function of temperature 2, and H2S, the H right here, is a function of T2S, of course. Now, there are two categories of these problems in general. One, you'll be given that the isentropic exponent K, N is equal to K, and K is somewhere around 1.4 for air. Offhand, I don't know what it is for the other gases, but generally it's 1.4 or 1.401 or something like that. It's actually the ratio of the constant pressure specific heat over the constant volume specific heat, but you don't have to worry about now. But if we're given K, then we know T2, and we can calculate T2S from this relationship. You've done it on problems now. And then we have to be given one other thing. We either have to be given the isentropic efficiency of the compressor, or given perhaps the exit temperature. We have to be given one. If we're given N equal K, we can calculate T2S. That should be T2S right there, by the way. We can calculate T2S from this expression. If we're given the adiabatic isentropic compression isentropic efficiency, we can calculate H1, which H2, I'm sorry. If we can calc from this, we get H2S, get H2S, get H, I'm sorry, from this we get T2S, get H2S from the tables, and then from this expression, we can get T2 and we can get H2. All right. If you're not given K, then there's another way. If K is unknown, then you can take this equation for entropy change for an ideal gas, which is equation 620A on page 186, and introduces something new to us, S0, the S0 function, which is the entropy change of an ideal gas due to temperature effects only. But unfortunately, entropy is a function of both temperature and pressures. So we just can't look up entropy directly as we can enthalpy. Enthalpy and internal energy are a function primary only of temperature. Primary only, that's not a good statement. There, as far as we're concerned, enthalpy is a function of temperature only. However, entropy is a function of both temperature and some other things, either specific volume or pressure. Since we're generally given that a form of S2S, S2 is, well, here's the way the formula reads. S2, when you know temperature 2 and pressure 2, minus S1, when you know temperature 1 and pressure 1, that's the entropy change. And it's equal to the S0 function at T2 minus the S0 function at T1 minus R, the gas constant, times the natural log of the pressure ratio, which we're generally given. So let's look over at our tables now. Let's look at, I think this is going to be on about the last page. Well, this is for air in English units, but it's the same for metric units, the same structure. So we look over here and we got temperature in degrees K. We got H. We know H is a function of temperature only, so the H values are given, the U values are given. But look, here are the S0 values. That's not the whole story for entropy of the gas at 360 degrees. That's the entropy due to temperature. You also have to come over here and account for the entropy change due to the pressures. And there's also a similar formula for temperatures and specific volumes. It's right under this, I think it must be equation 620B or 621. We're not using it here. Okay, so we have this equation. We can look up S0 at T2 and S0 at T1. Now, if we're looking for S0, okay, we're trying to find T2S. And I probably should have put an S right here. And we know the entropy is constant. So what we can do, we know T1, so we can look S0 of T1. We know P1 and P2, so we know these, and we know R for the gas, for air is 0.06855 BTUs pound mass degrees R. I don't remember what the metric, okay, so we set this half equal to 0, and we saw for S0 of T2 when there's no change in entropy from 1 to 2, so this has to be 0. So we know all of this, so we solve for S0 T2 right here, and let's call that now S0 of T2S, because the S entropy constant state is we're looking. So we've got this equation, we know this. So we can calculate S0 of T2S. And then once we know it, we can come back over the table and look for S0 T2S. And of course, it's going to be at a higher temperature than our initial temperature. Once we find it, we just look over to the left and read the T2S as the temperature. But it's not generally as easy as that, because it is just almost always going to require an interpolation. So let's work a problem out using this. No, we're not ready to do that. I'm sorry. Or are we? We got just a little bit more to go. So, I got page twos. Oh, I should have deleted this page. It's the same page. It's just when I scanned it in, I had the corner turned up. So I'll make sure what you get doesn't have this redundant page. All right, let's look at a problem. And this is going to be similar to what you're going to have to work on the test 3 that I'm going to be giving. This is an example of an ideal gas compressor compressing air. So we're given that P1 is 1 atmosphere, T1 is 520 degrees R. You know, that's actually 60 degrees F. We add 460 to it and we get 520 degrees. Always got to have these temperature, work with ideal gases. You've got to have absolute temperatures. All right, so we go through this compressor and we given the adiabatic efficiency of this compressor is 80%. Or we could have been told that this compressor has an efficiency of 80%. That essentially is the adiabatic isentropic reversible efficiency. Now our discharge is 3 atmospheres. So, and that's 3 atmospheres, whether we're dealing with the T2S temperature or the T2 temperature. And we're asked now we're not given a flow rate through this compressor. So when you're not given a flow rate, you're going to be working out the works and everything as a per pound mass. So we're asked to find the actual work of the compressor per pound mass and the actual entropy change from state 1 to state 2, and that's specific entropy per pound mass. Those are the 2 things we got. And we're given, it's adiabatic isentropic, and if it's 2 of the adiabatic isentropic, has to be the 3rd, which is reversible. If it's adiabatic reversible, it's isentropic. If it's isentropic reversible, it's adiabatic, and so on. We're given, I probably should have used a C subscript. We're given N of S, that's 80%. That's this adiabatic compression, adiabatic isentropic efficiency of the compressor. But we're given K is 1.4. Yippee, that makes it easier. So with K known at 1.4, we can use this equation to find T2S. T2S is equal to 520 times P2 over P1, which is 3 atmospheres over 1 atmosphere, which is 3. 1.4 minus 1 over 1.4, and we find that T2S is 711.74 degrees. Now I look at this formula here for the isentropic efficiency. We know what NS is 0.8, but it's equal to H1 minus H2S over H1 minus H2. Now I have to stop and think here. Make sure I've got the denominator and numerator right. You want the biggest number on the denominator because efficiency is always less than 1 or 100%. So for a compressor, it always takes more work than the isentropic work. You always have to put in more work than the isentropic reversible compressor would take. So when you think about it, you know that H1 minus H2S is equal to H1 minus H2. I know the book has these reversed as H2S minus H1 in order to make them both positive, but it doesn't matter because this is the way they actually come out in the first law equations. So I think it's more proper. Plus you're gonna have a minus over a minus, so you're gonna get a plus. Okay, and I forgot to write out the equation for the work actual of a compressor. It's the mass flow rate times H1 minus H2. Well, we aren't given the mass flow rate, so we're going to work per pound. Well, the rate of work per pound mass is just simply H1 minus H2. That's the actual work. But we don't know H2 now. So, and we don't know, well, we do know T2S, but we don't know H. Well, let's look. Okay. I found T2 is 711.74. Now, I went ahead and interpolated exactly to get H. This is H2S is equal to H of 711.74 degrees. I interpolated the tables. Let's look at the tables here. Oops, sorry. So, I hope you can see that. Let me blow it up a little bit. So I'm at 711.74 degrees. So I'm between 700 and 720. So I'm looking for H2S. So at 700, my H is 167.56. Here's 700, 167.56. At 720, my next tabular value is 172.39. So I just interpolate using y1 plus y2 minus y1 or x2 minus x1 times y minus y1 minus y, and I get 170.39 BTUs per pound mass. That's H2S. Now I still need H2, but I know that N sub S or eta sub S is 0.8. So I can just solve that equation there for H2. That'll be the only enthalpy. I need three enthalpies, H1, H2S, and H2. I've got H1, just got H2S. I can use this equation to get H2, and H2 comes out to be 181.92 BTUs per pound mass. So now I've got everything I can start going. So now to calculate my work per pound mass, it's just H1 minus H2, which is minus 56.75 BTUs. And I actually should have rounded that off to 56.8. So that's a -1 for me. And now I need to calculate S2 minus S1. I need to calculate, I've asked for the problem asked for the change in entropy. So I can use this equation. I got everything I need, right? No, I don't have T2. Now I need the real T2, not the isentropic, and the real T1, and the rest of this equation to calculate S2 minus S1. So I need to go back to this table I had here. No, what am I looking for? I'm looking for S0 of T2. Oh, okay. TR. Oh, this was H2. Okay. I'm getting confused here. That was H2. Okay. Okay. I interpolate here from H2S. Then I solve this equation for H2, but I don't know what T2 is. I know what H2S is. I know H2S is, I'm sorry, doggone it, I need an editor. I know I confuse you folks. Let me back up. I calculated T2S from this equation. Then I know in T2S, well, I calculated T2S, I went in and interpolated in the table, interpolated for H2S, okay? But I also need H2. So to get H2, I use the efficiency equation. Right here. Calculate H2S at 181.92. Well, I know H2, not H2S, H2. Calculate H2 from this equation. I know H2. but I don't know T2. And I need to know T2 before I can use this equation, because I have to look up S0 at T1 and T2. So I know H2 is 181.92. Let's look over at the tables. 181.92 falls between here and here, between 740 and 760. So I put 740 and 760. Now I'm also going to need S0 of T2. So why not go ahead and set up the interpolation from S0? In fact, S0 is really what I need. I may not even need to get T2, but I think it's good practice to do it. So using the same type, now look at these two and calculating and interpolating for T2, I get T2 is 759.34 degrees. And it's interesting to compare T2 and T2S. Let's go back and look at T2S. In round numbers, 712 degrees. T2, 759 degrees. So that's what, about 47 degrees more temperature rise because of the inefficiencies, the irreversibilities in the compressor itself. Okay. But what I really need is S0 too. So I interpolate, look at the tables. 181.92, it's right between here, 740 and 760. Well, at 740, S0 is 0.067665, and at 760, S2 is S0 is 0.68312. So I interpolate between those two and get 759.34 degrees. Now I've got everything I need to plug in my equation to get S2 minus S1, or delta S, again, per pound mass. Now I go through the calculations and I get S2 minus S1 is 0.159, and I think there was another digit out there. I rounded to 0.160 BTUs per pound degrees R. And it better be a plus. If I get a minus here, then I know I've gotten something wrong, because clearly from even our sketch, from even our sketch here, we see that entropy increases. S2 is on the right side, and so the entropy goes out this way. All right. Okay. Now let's look at a power cycle. We're going to look more after this test, but we need to look a little bit right now. I'm going to take a sip. My mouth's getting dry. Let me look at the share screen again and make sure it's all right. It shows that you're seeing what I'm seeing. Okay, that's good. So here's a power cycle, and the basic, by the way, all these cycles are really quite simple. I'm going to try to scale this down a little bit where you can see. All right. So here's the four elements of a basic power cycle. The boil, well, let's start at the turbine. The turbine, that's your workhorse. That puts out the work to drive your generator. The condenser, that takes this hot, low pressure vapor, or mostly vapor, and condenses into water. And that, as you see here on the TS diagram, I'll move this up where I don't have any control over that. I could probably figure out how to get rid of that. I'll do that next time. Anyway, you see the four element. Okay, I got through the condenser, which condenses, turns vapor and liquid, or all vapor or mostly vapor, into a liquid, and it goes through the pump. As you can see, this condensing is taking place at a very low pressure, in this case 0.08 bar. And we need to get up to this constant pressure line of the high pressure, which is 100 bar in this case. So the only way we can get a fluid from a 0.8 bar up to 100 bar situation is to pump it up there. So we pump it up, this liquid, and it has to be liquid for a pump to pump, otherwise it's going to do what we call cavitate, and it's going to tear itself up trying to pump a liquid and a vapor. That's why we have to turn all of this vapor into liquid over here to pump it up. Pump it up from, in this case, 0.08 bar to 100 bar. And here's the 100 bar constant pressure line. Here's the 1 bar constant pressure line. These are TS diagrams, nothing to be scared of. They're really nice. The constant pressure lines look just like they do on the temperature specific volume line. So, and in all of these power cycles, you're going to have this low pressure boundary on low pressure, and this boundary up here on the high pressure. Now let's go through each one of these. Once we get we going through the boiler and we're adding heat at constant pressure, and our temperature through here is the saturation temperature, which is 311 degrees. But as soon as it turns into all vapor and starts up in the superheated region, temperature go up, 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 until it gets up to the point where we want it. Our controls, our process controls stop it at 520 degrees, and now it's ready to go in the turbine at state 1. So our turbine, we use isentropic turbine expansion as our baseline, our goal, our measure of the ideal turbine. And so it expands ideally at constant entropy, straight line up and down to 0.2s. In actuality, entropy increases. Again, this area under this triangle here is the heat transfer that's lost. It's actually work that's converted into heat that's lost into the atmosphere. Here's the actual expansion process down to state 2. Now, sometimes this state 2 hits over here at the saturated liquid line. It may actually hit a little bit out here in the superheated zone, but generally it hits in here where there's a quality of 95, 90, or whatever percent. Just looking at this, the isentropic looks like it ends with a quality of about, you could say 80%, I don't know. And here, it looks like it might be 95%. So, and then once we get to the turbine process, go through it, we always hit at the same pressure, whether we go the isentropic line or the actual line. We just see the entropy increases in actuality. But once we get to point state 2, we go through this condenser, and using external cooling water that doesn't touch this hot water now, it's a heat exchanger. We call it liquid to liquid heat exchanger. We actually condense this. Here it looks like it's 50% vapor, 40%, 30%, 20%, all liquid right here. And we try to end this condensation process right here. It's saturated liquid. Then we go through a pumping process, and here's again, pumping process is a work process, sort of like a compressor, only we got liquid water. We don't actually compress it. We just move it from a low pressure to a high pressure region. But you can see here's the isentropic pumping process, 4S, and here's the actual pumping process, 4. Anyway, we pump it up to this high pressure line of 100. Now it starts through the boiler and picks up the heat. So through the boiler, we get QH, and the condenser, we reject QC, and the turbine work, we get out work WT, and the pump, we have to put in work WP. So there's a process. It's not a basic power cycle. It's not a complex process. Now the equations are really simple. The actual turbine work output is m dot times H1 minus H2. if you write out the first law equation, you will have on the left hand mem dot times H2 minus H1 equals Q minus W. Well, Q is 0 and you got a minus W, and if you get the W on the other side, flip-flop things around, you'll get the turbine work is m dot H1 minus H2. The turbine isentropic work, which is going to be more, is H1 minus H2S. The pump work is going to be the same m dot times H3 minus H4. QH is going to be m dot times H1, should be H1 minus H4. Yeah, that should be a 4, it doesn't look like. And then QC of the condensation heat transfer is H3 minus H2. And the thermal efficiency of the cycle, of course, it is limited by the Carnot temperatures. In this case, by 520 on the top and looks like about 93 on the bottom. And if you work that out, that's not going to be a very, maybe 50% possible. I don't know. Should have done that. Now, don't get this. I put a T over here for isentropic, I guess. I should have put a S. Well, this is the isentropic efficiency of the turbine, H1 minus H2 or H1 minus H2S. Notice that H1 minus H2S is now in the denominator. That's because your isentropic work, being work you get out, is more than what you actually get. It's just the way life works. The ideal work is say 100 units, and the actual work is maybe 75 units. So you better make sure your efficiency ratio has the smaller number on top. I have to stop and think myself when I'm working on one of these problems. Okay, let's work a real problem, a turbine problem. Okay, we're given that the high pressure going into the turbine is 100 bar, the temperature is 520 degrees C, and the mass flow rate is 10 kilograms per second. Coming out of the turbine, the P2 is 0.01 bar, and the quality coming out of the turbine is 90%. And we're asked to find work of the turbine isentropic, that's what the S means, work of the turbine actual, and the isentropic efficiency of the turbine. All right. So let's start looking at enthalpies, because we know we have our mass flow rate, we just need the enthalpies to make our calculations. Well, H2, okay, H1, we can look directly up in the table. Let me just go find, let me move back. H1 is 100 bar and 520 degrees. That's going to be right. That's going to be on this table, I believe. Okay, 100 bar. There's 100 bar. Maybe I could boost this up, the size a little bit. There's a 100 bar mini table, and we're looking for 520 degrees. There's 520. So H1 is 3425.1. 3425.1. Okay. What is S1? I'm going to also ask you to find S1. Well, S1 is right over here. S1, the entropy at state 1 is 6.6622, and the units are kilojoule per kilogram, the same as the enthalpy, except there's a K in that new denominator. It's kilojoule kilogram K for entropy. So we can look both of those up. They're quite easily done. Now H2, we know state 2 we were given is 0.1 bar and X2 is 90%. So we use our quality equation where H2 is equal to H of F plus X times H of G minus H of F, which is H of FG. H of FG, as I mentioned, is tabulated for you for enthalpy, and I think that's all. All right, let's see where we're working. We're working now in the saturated table because we've got a mixture. I think that's on page 1. And we're at what pressure? Okay, 0.01 bar. Okay, there we go, 0.01 bar. H of F is not 191.83. I didn't even write it out, did I? No, I must. 0.1 bar. Looks like I looked it up wrong, y'all. %, 1 bar. 0.1 bar. What did I look up? I looked up 251.4. I got on the wrong line. I'm very sorry. That's what you have to do. So let's change our problem to 0.02 bar. Actually, I wrote it down as 0.2 bar. I just got off here. -5. So let's work at 0.02 bar. My mistake. So at 0.2 bar, HF is 251.4. Make sure you're in the enthalpy. Do as I say, not as I do. 251.4 is H of F. H of G is 206.97. And I need H of F, H of G minus H of F, but it's calculated for me. It's 2358.3. So I can go through that simple calculation and I get H2 is 2373.9. Now I don't want to write out a bunch of decimal points. I just want to have the same amount as in my tabular value, which was 1 decimal point. So I know the isentropic turbine efficiency equation is H1 minus H2 or H1 minus H2S, but I don't have H2S. I don't have H2S. How can I calculate H2S? Well, what do I know about S1 and S2? For the constant entropy line, S2 is equal to S1. I looked up S1 up here is 6.6622, so I know that's also equal to S2. It looks like I went back to 0.01 bar. I'm sorry. So I know that S2 is equal to S1 is 0.6622. So this time I'm looking at 0.1 bar. Sorry about that. I know that S2 is 6.6622, same as S1 on the isentropic line. Now what I'm looking at, guys, is I'm looking at this point right here. I know this entropy here is the same as the entropy here. It's just the pressure is different. Big pressure drop. So I know the entropy is 6.6622. Now I'll look over here at my pressure. And like I say, I've gone back to the proper 0.1 bar. Look at what the SF is 8.1502 and SG is 8.1502 and SF is 0.6493. My actual entropy is 6.6622, so it is between those two. So I know I'm dealing with a mixture with a quality of X. So how do I calculate X? Well, X at 2S is just S2 minus SF at 0.1 bar over SG minus SF. And you know there's no SFG here, so I have to calculate SG minus HF. Okay, let's look at this. So S2, I know is 6.6622. What is SF? SF is right here, 0.6493. There it is right there. Then SG, what is SG? 8.1502. There it is. And SF is that same 0.6493. And if I go through the calculations, I find that X equality is 0.816, and I keep at least 4 decimal places. I actually put that in memory location A. You see my little balloon with an A in it. Now I can use the enthalpy quality equation to calculate H2S, knowing X2S is then X2S is just the HF at this point plus X H of FG. Well, what is H of F? Go over 1, it's 191.83. What is H of FG? 2584.7 or whatever. So go through that calculation. Look like 2392. Yeah, that's it. 2392 right there. Back to 0.1. Anyway, I get H2S is 210.0. So I have H1, H2, and H2S. So having those, I'm going to calculate my isentropic efficiency. H1 minus H2S, that's the bigger. No, I'm sorry. I have to double think every time. It's H1 minus H2 over H1 minus H2S. The H1 minus H2 is bigger work, is a smaller work. H1 minus H2S is a bigger work. Theoretical is always bigger of what you want. I want work. H1 minus H2S is bigger than H1 minus H2. So that if I forget how this equation goes, I know that's the way it is, has to be. I get 0.7993 or 80%, or 0.80 and percentage 80%. Now I can make all these other calculations quite easily. The work of the turbine actual is m dot H1 minus H2. I get 10.5 megawatts. The work of the turbine isentropic, 13.1 megawatts. That's quite a bit of energy. In fact, it sounds a little, but that's right. If I divide that by 0.8, I get 13. So that's 2.6 megawatts of energy going wasted as heat, unless you can use it to heat a building or something, but most times it's lost. So that tells me I sure wish I had could find a turbine with a higher isentropic turbine efficiency, and I think there are some higher than 80. Now, how much of this is a bonus question. If I ask you approximately how much energy is lost to heat? Well, it's simply the difference between the theoretical power and what I actually got out. Because if my turbine had been perfect with no irreversibilities, I'd have got 13.1. I got 10.5. Where did all that energy go? The vast majority of it, 95% or more, went in heat. So if I ask you that question to tell me approximately how much of the what is the heat transfer of the turbine based on the data you have, you would say it's the work of the turbine actual minus, I'm sorry, that should be an S, work of the turbine isentropic minus work of the turbine actual. All right, now this is the last cycle we're going to go through, heat pump cycle. Again, these cycles are not complicated, these basic cycles. Oh, when you start getting in, I took a whole course in refrigeration, and we didn't study this circuit totally. There were other circuits, but there's all kind of different things you can do to increase their efficiency. But this is the basic heat pump or refrigeration cycle. In this case, what we want is heat. So here's the elements of the cycle. Again, the main machine is the turbine. Brain dead. Compressor. So we're putting in work into this compressor to compress this refrigerant. In our case, generally it's R134A for automobiles and appliances. If you've got a refrigerator in your house or a freezer, it's using R134A. Your automobile uses R134A, and your air conditioning system for your home uses R410, or is it 416? I can't remember. R410A, I believe. So there's the actual circuit. Let's just follow it through. We start here coming out of the evaporator. Here's our flow through the evaporator from 4 to 1, and we come out, we got to come out at least here and maybe a little further. This is all vapor, saturated vapor. We might even come out a little further on this constant pressure. By the way, same as with the power cycle. Look, your cycle is bounded by two constant pressures. In this case, we chose 80 psi. That's a little low. Most times runs higher than that. But just for illustrative purposes, it's 80 psi on the top and 20 psi on the bottom. So bounded by these two constant pressure lines. So going in the compressor, we have to come out at least here and maybe even a little out in here, because the compressors will not compress liquid. If you come out of here with a liquid and try to compress it with a compressor, it's going to tear the compressor all to pieces. So what we're doing with the compressors, we're getting up to higher pressure. And in the case of refrigerants, just in the case of air compressors, when we go up in pressure, we get higher in temperature. In this case, that's what we want. We want a higher temperature, and we live with a higher pressure. We want the higher temperature, I'll explain in a minute. But here's the isentropic compression, straight line again, and here's the actual compression process. So we have state 2s and state 2, and as you can see, they're at different temperatures. 2s, I didn't mark what 2s is, but 2 is 120 degrees Fahrenheit. I suspect 2s is maybe 105. But again, this little wedge of work here is it's on the TDS, and remember, area under the TDS curve is heat transfer. So that is heat transfer. Looks like we just calculate that by calculating that little, integrating this numerically to calculate that little triangle, doesn't it? Well, it doesn't quite work that easy. One reason is this is not drawn to scale at all. And so that's really not, can't really do that. But you can find the compressor work theoretical and the compressor work actual and subtract them, and that's pretty much your heat energy loss to heat. But anyway, so we go through the compressor, our isentropic theoretical baseline, or our best case process, reversible process, adiabatic, reversible, isentropic is a straight line. The actual compression process increases entropy, ends up at state 2. But regardless, we end up at this pressure of 80 psi in this case as an illustration. We go through the condenser, and this is where the heat, this is really hot fluid. It's hot, and it's got a lot of pressure energy to it. It's got a lot of energy. And when we go this condenser, all of that energy is most of it is turned into heat. We get a lot of heat that we can pump into an area we're trying to heat, which is exactly what we want to do. So this is our QH, and this time it's going outside. Then we go all the way through the condenser, and we end up with saturated vapor at the high pressure. And we go through a throttling process. This is a throttle valve. It's in a throttle process, you remember the enthalpy is constant. But we are able to drop down to the pressure we want to in our evaporator. So this is the H equals C line here, and we drop down to state 4, go through our evaporator, become saturated vapor at state 1, we keep the process going. Continuous. And our equations are fairly simple. Our actual coefficient of performance is just QH over work of the compressor actual. That's how many units of heat I'm getting out for every unit of compressor work I put in. And a heat pump, at first thought, you'd think would be more efficient than an air conditioning system, because this work the compressor puts in to bring the energy level up to here is good in our case, because we can get most of it out in the form of heat. So the heat we put into the compressor, that goes to heat the end of the fluid, we can get back out, most of it. Equations are simple. The work of the compressor actual is m dot H1 minus H2. The work of the compressor isentropic is m dot H1 minus H2S. And let's think about our isentropic efficiency. So we're putting in work here, and isentropic you always have to put in more work, real work, than isentropic. So the real work equation has to go on the bottom. It's the bigger one, H1 minus H2, and then the numerator, H1 minus H2S. Okay, now let's work this problem, a real compressor problem, and we're done. And looks like it's just one page. Let me go ahead and get over the R134A here. Here's our R134A, and look like we're in English units here. Huh. I thought I did a metric, but I did another English. Sorry about that. I don't think I have that table. Nope. Yeah, I do. I have both. All right, I do. Let me go up and check share and make sure you're seeing what I'm seeing. You're supposed to be. Okay, there's my R134 saturated table. Now let's see what we got over here. All right, we got a compressor, air conditioner, or heat pump compressor, either one, heat pump in this case. It's getting R134A as saturated vapor at 30 psi, 30 pounds per square inch. And that's absolute pressure. All pressure is absolute. The mass flow rate is 0.1 pound per second, and we're compressing it up to an exit pressure. Actual conditions on the exit are 80 psi and 120 degrees F. And we want to find H1, H2, H2S, isentropic compressor efficiency, the work of the compressor actual work, and the isentropic work of the compressor. All right, so we start looking up stuff. H1 is H of 30 psi in saturated vapor. Just a real easy to do. Here's 30 psi. By the way, the temperature at 30 psi is pretty cold. That refrigerant is at 15.38 degrees F. 30 psi, and we want saturated vapor. So HF is 103.96. Now notice how much smaller numerically these are than steam water. That doesn't necessarily mean that this has less energy. Well, actually it does, but the reason there's so much difference is because they're different reference point, I'm sure. But you're probably right. There's a lot more energy in steam water than there is in this Freon, or R134A. So there's H1, 103.96. I'm sorry, H1. What did we look up here? 30. Should be 16.31 right here. I looked at HF. No. Something's wrong. Oh, H1. Yeah, I looks like I worked that problem wrong. So that's amazing I did that. One has got to be saturated. Oh, brain dead, Larry. I'm sorry. We're at 30 psi and we're saturated vapor. Sorry. HG. Compressors won't compress liquid. So we're at 30 psi. HG is 103.96. But I looked up the wrong thing though, didn't I? I looked up H2S. Yeah. I'm going to have to rework this one. I'll rework this, correct it, and I think I'll do a metric problem. So I'm going to stop the video right here, and there'll be a part 2 this one where I go back and rework this problem. Sorry about that. I guess I'm just wasn't concentrating properly. Let's see if I got H2 right. 80 psi at 120 degrees. Now that's going to be saturated. That's going to be superheated. No, I don't think I got the table back. Well, I'll correct this and I'll be back with you. Hang in there with me. We'll get there. I'm very sorry about this error.